This is a brick office. Actually, my office was once upon a time a women's dorm room, and it has been repurposed. Sometimes you can kind of still tell. Let's do our last method, the third method. This is a mathematical approach to using conditional probability, and I've purposely done it last of the three methods because I have a lot of students who say, I just want the equation, just tell me the math. And the fact is, when you get into the equation, you're not sure what it means and how to do it, and some of the other methods really work better. But here's what the mathematical equation for what we've been doing would look like. And this is ugly. What's the probability of A given that you know B? Well, it's the probability of A, and then the probability of that B under the A scenario. And on the bottom, you have to add up all the different ways that you could get B under some scenario times the probability of that scenario. Way confusing. In our case, we've been talking about two different scenarios, which means we can at least simplify this by doing that. And what this says is we want the probability under the A scenario and the probability of B under the A scenario. It's the same thing we have in the numerator, which is why what's in the numerator always shows up in the denominator. And then here we have the not A scenario. And what's the probability of B under the not A scenario? But this whole given notation tends to be confusing. I've seen some books use notation that looks like this, and it's a little simpler. We have what's the probability of B happening under the A condition, and the probability of A. What's the probability of B happening under the A conditioner, and the what's the probability of B happening under condition A times probability of condition A. And here we have the probability of B happening not in condition A, and the probability of not condition A. So that still might be confusing to you unless we put it in context of what we were talking about. For the breast cancer scenario, we have what's the probability of cancer given that the test was positive? Well, on top we're going to put the probability of cancer and then the probability of the test being positive. There's two different probabilities for that. We have a probability for cancer and a probability for not cancer. Well, this is the cancer scenario. So I want the probability of the test being positive in the cancer scenario. In the bottom, it's going to be the same thing. The numerator always shows up as a possibility in the denominator. Here we have the probability of the test being positive under the cancer scenario and the probability of cancer. And here we have the probability of it being positive when there's no cancer and the probability of no cancer. So putting these numbers in, we get our probability of cancer is 0.0147. Probability of the test being positive if you have cancer, there's the 0.192. Now the probability of not cancer, that's 1 minus the 0.0147. What's the probability of the test being positive if you do not have cancer? I'm going to take this number and take 1 minus it. So you can't just blindly throw numbers in here. You've got to think for a minute. What's the probability and how does that relate to my sentence? Okay, I need to take 1 minus. There you go. When you calculate this out, guess what? You're going to get 0.3737. That's actually what we already did. With the tree diagram, we multiplied these two numbers and then had them out. With the counting method, we multiplied these numbers times by 1,000,000, but numerator and denominator was all 1,000,000. So whatever method works for you is great. If you like this method, let me remind you that when you put this in your calculator, you'll want to put round brackets, an extra set right there on that denominator so that your calculator will divide by the whole denominator. And I think that's way too hot.